In our last video, we began our example using a one-way analysis of variance to test whether there were differences in mean ratings for hamburgers across three different chains: Burger King, McDonald's, and Burger Shot. We posed our hypotheses, looked at the raw data, and began this series of analyses needed to calculate our F statistic. We got through the within group components, and in this video we'll now determine the between group sum of squares, degrees of freedom, and variance, as well as the F, the p-value, and our statistical and substantive conclusions. Now, to start, let's calculate the sum of squares between. To do that, we first go all the way back to our group means. Remember, these were 2, 4.5, and 7. We then subtract the grand mean, which was 4.917, from each of these. So let's list the three group means, right? We then subtract the grand mean of 4.917 from each of these. That gives us 2 minus 4.917 for Burger King, 4.5 minus 4.917 for McDonald's, and 7 minus 4.917 for Burger Shot. If we solve those, that gives us our group mean deviations from the grand mean, which are negative 2.917 for Burger King, negative 0.417 for McDonald's, and 2.083 for Burger Shot. We then square these group mean deviations from the grand mean. Now, remember, when we discussed partitioning the sum of squares, these values, these squared differences between one's group mean and the overall grand mean, applied to every person in the data set. So we have to weight each of these by the number of people in each of the corresponding groups. You can think of that this way. Each of the three Burger King people has a squared group mean deviation from the grand mean of 8.507. Across all three of them, that sums to 25.521. And each of the four people in the McDonald's group has a squared deviation between their group mean and the grand mean of 0.174, which across all four of them sums to 0.694. And each of the five people in the Burger Shot group has a squared group mean deviation from the grand mean of 4.340. Across all five of them, that sums to 21.701. Yes, your values may be a little different due to rounding. That's okay. We then add each of these squared deviations to obtain the sum of squared deviations between groups, or the sum of squares between, which is 47.917 for this example. All right. We then enter this into its space in our ANOVA table. All right. Let's keep going. The degrees of freedom between is simply the number of groups k minus 1, which in this case is 3 minus 1, or 2. Let's then enter that into our ANOVA table. All right, and we'll keep moving. The last step for our between groups calculations is to determine our variance between. As with the variance within, you may see it reported as as the variance between, as s squared between, or as the mean square, or ms between. It's all the same thing, the between groups variance. Now, we get that, right? Remember how we get that? We get it by dividing the sum of squares between by the degrees of freedom between, or 47.917 divided by 2, which gives us 23.958. Again, with rounding, I'm using non-rounded values here in my calculations. Let's add that into our ANOVA table. All right. And notice we're steadily deriving all of the information in the ANOVA table. We're now ready to calculate our F statistic, and to get that, we just divide the variance between by the variance within, which is 23.958 divided by 1.889, which gives us an F of 12.684. All right? We then add that to the ANOVA table, and we're almost done. Now, remember to report the F using the proper notation. Don't just say F equals 12.684. Include the degrees of freedom and report it as F with, in parentheses, 2 and 9 degrees of freedom equals 12.684. Don't forget the degrees of freedom in parentheses. Now, before moving on, let's enter 2 more cells into our ANOVA table, the total sum of squares and the total degrees of freedom. These ones are easy. First, the total sum of squares is just the sum of squares between plus the sum of squares within, or 64.917. And the degrees of freedom total is just the sum of the degrees of freedom between plus the degrees of freedom within, or 11. All right? So we have our F statistic, and the only thing left in our ANOVA table is now the p-value. So to obtain the p-value, all we do now is enter that F statistic of 12.684 with 2 and 9 degrees of freedom into Excel or some software, or look it up in a book to find the p-value. But let's actually take a closer look at the F distribution and our F score. So here's the F distribution with 2 and 9 degrees of freedom. If the null is true, this reflects the distribution of F scores we would expect to see randomly if we sampled the same number of people from the same populations over and over an infinite number of times and just had that random variability sample mean to sample mean. So now if we look up the critical F score for an F distribution with 2 and 9 degrees of freedom based on our alpha of 0.05, we'd find that that's equal to 4.256, which means that only 5% of the distribution is more extreme than an F score of 4.256. Again, this is all based on the null being true. If the null is true, getting a result more extreme than an F equal to 4.256 is so unlikely, we'd conclude that the null probably isn't true. So we reject the null. In our case, our observed F, the F we obtained in our data, was 12.684. That's more extreme than our critical F, right? It's in that region of rejection. So we know the probability of getting this result, if the null is true, is less than 0.05. We'll reject the null hypothesis. All right? But what's the exact p-value? What's the exact probability of getting a result this extreme or more extreme if the null is true? Well, if we look up that f of 12.684 with 2 and 9 degrees of freedom, we see that the area more extreme than 12.684 is equal to 0.002. That's our p-value, right? Now with that, we're ready to complete our ANOVA table. All we need to do is insert that 0.002 for our p-value, and there we go. All right. Now, we can also see, again, down here, remember how to report it. Remember your parentheses, and we're including the p-value in this case. All right, so we kind of summed up here. So I think at this point, we're ready to wrap up our results. Now, here's where we started. Our research question of whether the ratings for hamburgers from the 3 different chains were different, right? So we've got our research question. Our null hypothesis was that the mean ratings in the population of people eating at these 3 restaurant chains were all equal. And the alternative hypothesis is that the means for those populations of people eating at these 3 restaurant chains are not all equal. Right? Our statistical conclusion was that with 2 and 9 degrees of freedom, we obtained an f of 12.684 with a p-value of 0.002. We reject the null hypothesis. That leads us to our substantive conclusion that there is a difference in the hamburger ratings across that population of diners in these 3 different restaurant chains. All right? Now, remember, the F-test doesn't tell us which means are different from each other. It doesn't tell us which hamburger had the highest or lowest ratings compared to the others. It just tells us that the mean ratings are not all the same in the population. If you want to know more about which groups are different from each other, there's additional follow-up tests that you can do comparing one group to another group. All right, but that's beyond what we cover here. But we do talk about this in other courses and other videos, okay? Now, that completes this very simple example of a one-way ANOVA by hand. Hope you found it helpful. See you in the next video. Bye-bye.